What is that and how does it work? We have those questions to think for all kinds of things, like the periodic table of elements, this diagram, this formula, the phrase, what goes up must come down, and this 27-kilometer ring of superconducting magnets in Geneva. In other words, those are the questions behind almost everything we know and everything we're going to find out about the physical sciences. Hopefully, they can help us figure out what this thing is, too. Hi, I'm Callie Moore, and this is Study Hall's Physical Sciences Tune-Up. The physical sciences, at their heart, are about observing the world around us, with a focus on the non-living aspects of the natural world. This means the physical world right in front of us, from rocks to air to heat, but also more abstract things that underpin all that stuff, like how the parts of atoms interact, how matter and energy work, and how the rest of the universe beyond our planet operates. That's, well, everything. So it's all broken down into more specific fields within physical science. For instance, physics is the study of matter, energy, and the forces that guide their interactions. That involves things like mechanics, the study of how and why things move, acoustics, the study of sound, optics, the study of light, and electricity and magnetism. Then there's astronomy, the study of celestial objects, space, and the universe. And when the principles of physics are applied to astronomy, you get astrophysics. Think things like space-time, black holes, gravitational waves, the makeup of stars, dark matter, and how the universe began and how it might end. And chemistry is the study of the composition, structure, and changes of matter, or, stuff. That's where you'll see the periodic table and look at things like how a yellow-green gas and a silvery white metal combine to make table salt. Then when you go really deep into chemistry and physics, you might get into quantum physics and quantum chemistry, which study the stuff that can happen in the teeny tiny component parts within atoms. Things like how some forms of energy like matter and light can behave both like particles and like waves, or ways that particles can exist in multiple places at once. It's heady, mind-bending stuff. Or you can do something way more down to earth, like the earth sciences, which includes everything from climate science to geology. They help us understand exactly how Earth's composition and the atmosphere impact how we live on Earth and what we can expect from the planet as history continues forward. In other words, if you're interested in the physical sciences, you've got options. But it's not enough to just know what the physical sciences study. It's also helpful to understand how they study it. In our first Science Tune-Up episode, we talked about how the scientific method is a rigorous process of experimentation that's repeatable and holds up under scrutiny. And in the physical sciences, we can see that process clearly. The physical sciences are about empirical evidence, precise measurements, tightly controlled experiments, and long-standing repeatable outcomes and observations. These observations might be qualitative observations, like noticing that the stars seem to move in predictable patterns, or seeing that fire changes in color and shape based on what it's burning. These are the observations we make using our 5 senses: sight, hearing, smell, touch, and taste, rather than through measurements or numerical data. But the physical sciences often also require quantitative observations, where you collect numerical data to more precisely describe the differences and degree of change in the patterns you're seeing. That data may be collected with precise instruments, measuring anything from mass and volume to electrical currents or gravitational waves. And physical scientists aim to structure a measurement so that it will remove all other potential influences on the outcome except the variable that you want to study. Without using the correct, calibrated equipment and without a thoughtfully designed experiment, you might get errors or miss other explanations that might be the reason for the effects you observed. But we don't always have precise enough instruments to measure very tiny things or the ability to, say, physically measure the properties of a distant star. In those cases, physical scientists also make and use models. These might be computer models or simulations, physical models, or even equations that allow us to better study things we can't directly observe. They can also help us analyze and explain observations and experimental results or design solutions to problems. Physical scientists study many observations and models and attempt to discover and understand the natural laws that describe how everything in the universe works, and they develop theories about why those things happen. Now, a word about laws and theories, because in science, these words mean something different than they do in other spaces. And it's not like there's a hierarchy here. It's not that laws are more legit than theories or that theories are unproven, and once they get proven, they become laws. Instead, it's helpful to think of laws as describing what happens, while theories explain why something happens. So in the physical sciences, laws are relationships known to be true due to extensive observation and experimentation on the natural world. They're often written as equations that explain how nature will work in certain conditions. These are things like the laws of motion, which describe how objects move and react to forces, or the law of conservation of mass, which states that matter can't be created or destroyed in chemical reactions. Theories are also based on extensive observation and experimentation, and they explain why we observe the things we do. And while theories can and sometimes do evolve and change as new information is discovered, they can also be really well established and airtight. Take gravity, for example. The law of universal gravitation was described by Isaac Newton in 1687. And it states that all objects have a gravitational pull. It also gives us a formula for calculating the gravitational force between two objects. But there could be a number of explanations for why gravity works. Like maybe rocks and trees and humans just like to be on Earth, and birds and clouds like to be in the sky. Maybe everything has magnets inside that draw objects together, or maybe gravity is the bend in space-time caused by the mass of an object. That last one is actually our current understanding of what gravity is. It comes from Einstein's theories of general and special relativity, which he developed over 100 years ago, and so far, the evidence has supported them. It's taken hundreds of years and even more people to gather everything we know about the physical sciences. And even though the physical sciences deal with the fundamental, foundational stuff of our universe, we're far from having it all figured out. Take the periodic table. There's one hanging on the wall in just about every science classroom, so we're pretty familiar with what it looks like. But it hasn't always looked that way. This is an early table of elements presented by John Dalton in the early 1800s. This is what the periodic table of elements looked like in 1869 when Dmitri Mendeleev created another version. And many more discoveries and changes in the way we understand and organize elements have happened since then, including these 4 additions in 2016. We've even made our own elements, and some scientists are also still actively working on finding or making more new ones. So here's a closer look at part of the process of getting from here to here, and what it looks like to do physical science and build our knowledge of physical science. And you'll notice we're not just talking about one day or one person or even one discovery, but we're talking about using the scientific method over time to draw conclusions and build understanding. Way back in 1789, a German chemist discovered the element uranium, which is here on the periodic table. An element is a substance that contains only one type of atom. They also have unique properties, like their melting point and how they interact with other elements. But at the time, we didn't know much about those properties. So in 1896, when the physicist Henri Becquerel sort of accidentally discovered that uranium salts could emit spontaneous rays, no one really knew what was going on. Soon after, doctoral student Marie Curie was beginning to work on her thesis, and she wanted to investigate those rays further. First, she did several experiments that confirmed Becquerel's observations and conclusions. elements. Using an electrometer, she measured faint currents in the air that had been exposed to uranium, and she found that uranium emitted constant rays whether the uranium was wet, dry, solid, pulverized, or exposed to heat or light. Then she built on those observations and conclusions. She hypothesized that the uranium rays were a property of the element uranium, which she called radioactivity. And this completely changed how people thought about atoms. At the time, scientists thought atoms were solid, inactive, and unchangeable. But Curie found that radiation was emitted by the atom itself, and that atoms are made up of smaller particles that can move and change. And she didn't stop there. She wanted to know if other substances had this property. And she found that two of the uranium ores she'd been working with, called pitchblende and chalcolite, were more radioactive than pure uranium. She concluded that this was because the ores contained one or more other radioactive elements that no one had discovered yet. So she set out to discover the element. Eventually, in 1898, after a long process of grinding samples of pitchblende, dissolving them in acid, separating their parts, and measuring their radiation, she and her husband, the physicist and chemist Pierre Curie, published their conclusions. They had found not one, but two new radioactive elements, which they named polonium and radium, and which show up here and here on the periodic table. To further prove that these were new elements, Curie worked to isolate pure polonium and radium. After 3 more years and several tons of pitchblende, Curie successfully isolated 1/10 of a gram of pure radium chloride. She eventually isolated pure radium as well, but she never managed to isolate polonium. It decayed too quickly. Still, the Curie's work would go on to be instrumental for all kinds of other things. Their understanding of radiation paved the way for the development of nuclear energy. They also found that radiation from radium killed diseased cells faster than it killed healthy cells, which became an important part of cancer research and treatment. And their understanding of radioactive decay became useful to Earth sciences. It's how we came to figure out Earth's age. Curie's work is just one example of the kind of work that happens in the physical sciences, but it shows a lot about how that work happens. It requires precision, delicate measurements, curiosity, repeated experiments, and failed experiments. It takes years of work that build on the years of research, observation, experimentation, and curiosity that have come before. And then other people get to take that work and keep building on it to make new observations, developments, and discoveries. Which means there's still plenty of room for more experimentation and research within the fields of the physical sciences. There are all kinds of big, exciting, open questions in physical sciences and discoveries to be made about things like dark matter, quantum computing, Earth's magnetic field, and the elements on the periodic table. So if you want to know more about just about anything, the physical sciences are a really great way to do that. If you're currently in or thinking about going to college, go to gostudyhall.com for more student resources and check out our $25 college courses. Thanks for watching. See you next time.